Alright, so now we get into one of my personal favorite parts of this course and the progression in learning quantum computing, which is touching on the idea of tensor products and, how it relates to entanglement. Now, quite simply, when you look at entanglement, we are essentially looking at multi-qubit systems. Multi-qubit systems. Multi-qubits systems and their states. Now, in order to represent these lovely multiple qubit systems, right, we've got to have some way to connect them. We've got to be able to say, hey, we have this qubit here, we have this qubit here, how do they affect one another? Or in other words, how are they entangled? Or alternatively, if they are unentangled, how do these qubits exist relative to one another? We've got to have some sort of mathematical representation to do so. Now, in order to do that, however, we've got to touch on a couple of previous concepts, things that you probably have seen before, perhaps in algebra or something of this sort. Now let's talk a little bit about probability first. So just topic 1, let's dive a little bit further into probability. Now you may be familiar with the typical coin flip problem, I apologize, and with the coin flip, right, when you want to flip a coin, you either get heads or tails. Now when you have heads or tails, you're like, alright, so this is pretty straightforward for each one of them. Assuming they occur with equal probability, we end up with a 1/2 and a 1/2 chance for either one. Now let's say on the side you also want to spin a wheel, and this wheel here has a total of 4 sections, and they've been labeled A, B, C, and D. Now each of these sections occur again with equal probability. So if I spin the wheel, I have a 1/4 chance of getting an A, a 1/4 chance of getting a B, 1/4 of getting a C, and so on and so forth, and it applies to the last one. Keep in mind here, the probability is also just always for these two separate events here, right? They will always add up to 1. 1/2 and 1/2, that equals 1, and a quarter plus itself, a total of 4 times, is going to be equal to 1 as well. Now keeping that in mind, let's talk about what happens if you want to both flip a coin and also spin the wheel. We want to talk about the combinations of events that occur. And you can see here where I'm kind of drawing this parallel here to multiple qubit states. In this case, we are considering what are known as sort of independent events, meaning regardless of what the result of my coin flip is, it's not going to affect what my wheel spin comes out to be. Now, these independent events, however, events can still be represented relative to one another. Now, generally, when you want to represent them, let's say we have a probability of events, we'll call this event E1, event E2, or the probability of event E1 of some sort and E2 occurring is going to be equal to the probability of E1 on its own multiplied by the probability of E2. So what does that mean in the context of, the situation we've just put before you? It's saying, for instance, if I want to say what is the probability of me both getting heads and also spinning on the wheel the letter D, right, that's going to be equal to the probability of getting heads multiplied by the probability of getting the letter D, which is going to be equal to 1/2 multiplied by 1/4, which comes out to be 1/8. Now, keep in mind here, we are assuming each one does occur with equal probability. That's where we get the 1/2 and 1/4 from again. And so, if we consider all the possible pairings, this probability that comes out does indeed make sense, because there are a total of 8 possible pairings: HA, right, HB, HC, HD. Then we have TA, TB, TC, and TD, right? And we have a total of a lovely 8 possible pairings, each that occur with equal probability. And thus, that means that the probability of a single one of these pairings occurring is equal to 1/8. And that indeed does make sense. So keep in mind, and let's remember this idea of multiplying their probabilities for the time being, because it will come back to us in a moment. Alright, so probability review aside, let's begin talking about qubits. So now recall when we said, with the idea of qubits, when we began to talk about entanglement, we wanted to say Alice and Bob wanted to send messages to one another. Now the question here is, in our initial problem, are Alice and Bob's qubits entangled? And this is a question that we will go forward and answer today. Now Alice here wants to send a message, and she's going to say, alright, so I'm going to measure my qubits in the following, using the following orthonormal bases. She's going to use a 0, right, and a 1. It's just going to use 2 in this case. And Bob, on the other hand, is going to measure his qubits in the directions B0 and B1. All right, and going on from there, just following typical convention, just kind of setting up the scene right here for what we do have going forward. Alice is going to say, all right, so she measures the qubits, and it's going to be represented in the following way. It could be represented, right, as a vector, let's call it V, as a linear combination, C0, A0 plus C1, A1. And similarly for Bob, let's call his the vector representing his particular qubit on his end, right? They each have a little qubit. The qubit on his end is W, and say it can be represented as a linear combination D0, B0 plus D1, B1. Now, if this seems like you need a little bit of a refresh, or if we just need a bit of a connection to what we just said about probability, keep in mind the numbers, right? D0, D1, and C0. C1 are known as your probability amplitudes, and so it is worth noting here that C0 squared is equal to the probability of measuring your qubit in direction A0. And thus, it can also be said that C1 squared is equal to the probability of measuring the qubit in direction A0, right? And so on, so forth. So hopefully this seems a little bit familiar, or, something that seems, at the very least, approachable. Now, we will keep in mind the fact that it is squared here, so this will come up in a moment. And so, going on from there, let's clear the board and briefly talk about what happens if we attempt to represent Alice and Bob's qubits in a multi-qubit system. Because previously, keep in mind, with each of these vectors here, we are essentially painting them in an individual light, right? Because this linear combination here does not take into account what Alice's is, and this in linear combination here does not take into account what Bob's qubit is measured as, in the probability of, say, A0 and B0, both essentially the probability of getting both A0 and B0, or the probability of getting A0 and Bob measuring his qubit and getting B1, and so on and so forth. So that is what we're attempting to determine, right? This is our end goal. We want to have some way of looking at a linear combination and saying, all right, so the probability of both Alice and Bob measuring their qubits in the direction A0 and B0, right, is going to be such and such. The probability of them both measuring it in direction A1 for Alice and B1 for Bob is equal to such and such, so on and so forth. So we want to determine whatever coefficient lies over here. We want to determine this probability amplitude. Alright, so let's clear the board and make it look a little bit neater. And so we end up with a very interesting type of operation, and this is what is known, as I said before, as the tensor product, because we want to be able to multiply. Right? We want to be able to multiply our two vectors. This is Alice's, right? And this here is Bob's. And we want to be able to, based on this multiplication statement, this product here, we want to be able to essentially take it and say, all right, looking at what we have here, this is going to be equal to some linear combination. Now, keep in mind, we're using a tensor product in this case largely because, like we said before, with that probability, we want to be able to multiply the probability of one event by the other. So if I was to write out the entirety of these vectors, it would look something along the lines of this, right? If we take Alice's vector, V, and just write it out, that would be C0, A0, plus C1, A1, right, multiplied by, and this little circle with the X inside, that is your tensor product sign in this case, and we'll simplify it down in a moment. But for now, let's just use this entire symbol here, right, multiplied, or finding tensor product of it with D0, B0, plus D1, B1. It's just rewriting what we had on the previous page. Now, if we were to multiply it out without me giving you any direct definition of exactly, what a tensor product is, we get and end up with something that looks a little bit daunting at first, which essentially comes out to be C0, D0, A0, B0, okay, plus, let's go with C0, D1, A0, B1, plus C1, A1, oops, I messed up the order there. Let's keep our probability amplitudes in the front, shall we? D0, and then we have A1, and then B0, plus last but not least, we have C1, A1, oh, same item here, alright, D1, A1, B1. All right, and that is what the linear combination comes out to be. Now, first of all, if you are familiar with what we have here, and let me really briefly make sure we have our tensor product signs in there. Tensor product. Keep in mind that for these, we are going to preserve the tensor product sign for now, largely because, again, it is a multiplication statement between our two vectors, right? V and W. And so we've got to preserve that operation. Of course, when you take two coefficients and multiply them together, it's still going to come out as a coefficient of some sort, and that is why we don't have a tensor product symbol between C and D in your vector in this case for the most part. Now, when we look at this, you may be familiar with it, and this is what is known as the FOIL method, F-O-I-L. And basically, the FOIL method, right, is looking at a way where you could take, some sort of statement, let's say x plus 2y, and multiply it by another expression. So in this case, let's say it is a lovely 3x plus y. Now, the FOIL statement essentially says that we say take x, multiply it by 3x, that would be 3x squared, right? This is basic algebra. Hopefully you're familiar, if not with the name, at least with the strategy. So x times 3x is equal to 3x squared plus x by y, right? So we go outside, and then we go in. So 2y multiplied by 3x, which is equal to 6xy plus 2y multiplied by y, which is equal to 2y squared. And this is essentially equal to 3x squared plus 7xy plus 2y squared, which hopefully seems a little bit familiar because, long story short, this is what is known as the FOIL method. This is basic algebra, things you probably have worked with if you've ever worked with, for instance, polynomials in terms of graphing, so on and so forth, or factoring, or even in calculus when you've worked with differential equations, for instance, you've still got to multiply it out just to make things a little bit easier for the most part to, for instance, differentiate or integrate. Now, going on from there, using this FOIL method, actually, we see that we've done exactly that in the tensor product. We've taken our two terms, right, and our two terms here, and we've multiplied it out essentially. So we've taken C0 and A0 and taken D0 and B0, and we've multiplied them together. Similarly, we've taken C0 and D1, multiplied them together, right? And we've taken A0 and B1, multiplied them together, result in the second term. And it goes on from there to result in this linear combination that we have below. Now, for simplicity's sake, and you may have seen I already started to do this a little bit earlier, we are actually going to simplify what we have up here. And just to make things notationally a little bit easier, and given that this idea of FOIL is pretty intuitive, if you are again familiar with algebra, we are going to replace this tensor product sign, and we're just going to say this right here, this vector v multiplied, and finding tensor of v with w is just going to be written as v and superposition it, right, position it with w, right? And so, and I apologize for my use of superposition there, that is a physics term, that is not what we're implying in this case. So just taking what we have up here, we're just going to rewrite it using the same kind of idea where the placement of these two vectors next to each other essentially implies that we're attempting to find the tensor product. So we have, again, C0, D0, and we have A0, right? And we're just going to place them next to each other. And then C0, D1, find the tensor product of A0 and B1 plus C1, D0, and take the tensor product of A1 and B0. And lastly, we have C1, D1, take the tensor product of A1 and B1. All right, so this is starting to look a little bit familiar, hopefully, at this point, right? Because it's pretty much what we have and have seen previously. Now let's take a look at what we have here and just kind of analyze it a little bit further. So let's take our first term, right? C0, D0, A0, and B0. That's quite a mouthful here. And let's talk about the probability amplitude. Now recall that the probability amplitude is referring not to our vectors, but instead to our two, or in this case, just our coefficient here. Now coefficient here is C0, D0. And what this here is describing the probability amplitude of us, or in this case Alice, right, measuring her qubit in the direction A0 and Bob measuring his qubit in the direction of B0. And so we're going to square that to find the probability, which is equal to C0 squared D0 squared, right? Just distributing, in this case, that exponent. Now, this may seem a little bit familiar because recall when we said earlier that the probability of getting A0, right? Probability of A0 is equal to C0 squared. And the probability, similarly, of getting B0, of measuring Bob's qubit in the direction B0 is equal to D0 squared. And thus what we actually have here is the probability, let's draw a little arrow here, right? Is the probability of getting A0 multiplied by the probability of getting B0. And you might say at this point, all right, that's cool. You know, where are we going with this? Now, if you recall earlier what we said, even earlier, just at the very beginning of this kind of lecture and this video, what we said earlier was that if you have two events that are ideally independent of one another for the most part, right, what we're talking about is when you want to find the probability that one event occurs and the other also occurs, we take their probabilities and multiply them by each other. So this is essentially equivalent to the probability of measuring your qubits in both direction A0 and B0, and thus, you know, the statement here does indeed come out to be true. And if you apply the same operation, squaring each of the respective probability amplitudes for all four of our terms, or just the remaining three that we have on here that we have not looked into, you will find indeed that it still follows the same concept of multiplying the probabilities of each of these individual of the probabilities of getting a qubit in each of these individual directions and multiplying them together, and you get the overall probability of having both Alice and Bob have the qubits come out to be whatever outcome, whatever pairing that we have in this case. And so it's kind of neat because with this idea of tensor products, you are essentially touching on things that you already know before. And what's even more interesting is it's just getting a new name. It seems daunting because perhaps the word tensor product is a little bit foreign, or perhaps, you know, it seems like it's introducing an entirely new concept. However, it's just applying what we know before and items that we already know previously to this new name and this slightly different notation. Alright, I've just cleared the board. So now looking again at this and what we have up here, let's continue to break it down a little bit further. We've already taken away that tensor product kind of sign here, but let's say we replace each of these. So let's say we take C0, D0, and we refer to it just here on out, just temporarily, as R. And let's say we take R, and what comes after R in the alphabet, we have S, right? And let's say that is equal to C0, D1. And on the other hand, we also have C1, D0, and we'll say that corresponds with T is equal to C1, D0. And lastly, let's say U corresponds with C1, D1. So we're just going to replace these with variables temporarily, again, just to clean it up by a little bit more. And so what we end up with is something along the lines of R, you know, A0, B0, so on and so forth, S, you know, A0, B1, etc. is equal to our initial vector V multiplied by W. Alright, so we aren't actually going to be looking at the linear combination in this case. I want you to focus instead a little bit more on R, S, T, and U. Based on what we have here, we already know that R multiplied by R, in this case, that R multiplied by U is going essentially to be equal and equivalent to the idea that U S multiplied by T. And the reason for that is if you again plug it back right into this equation that we have here, we have C0, D0 multiplied by C1, D1. This is again algebra. C is equal to ideally C1, D1 multiplied by C1, D0. And if we just rearrange the terms according to the commutative property of multiplication, something you hopefully are familiar with from primary school, for the most part, you can see that we're multiplying to C0 multiplied by C0, multiplied by terms D0, D0, C1, C1, D1, D1. Terms on either end match, and they're all being multiplied by each other in the same exact way, and thus this statement here holds true. Now, going on from there, we also know that R squared plus S squared plus T squared plus U squared is going to be equal to 1. And the reason for this, like we said before, is that the total probabilities of all of these items, right, out of the 4 possible events here, all their probabilities when added together must be equal to 1. And their probability amplitudes here are represented by R, S, T, and U, and squaring them gives us our probabilities of these events, and adding them together will be equal to 1. Again, this is basic probability. Hopefully, again, you are familiar with this. And so now, given that we know that R squared plus S squared plus T squared plus U squared is equal to 1, we now come to a slightly new idea. So now let me clear the board again and let me write out this entire format and this entire concept that we have here with R, S, T, and U, replacing their respective probability amplitudes. So now looking at what we have here on the board, we come across a number of quite interesting, quite curious I wouldn't quite call them revelations, but for the most part they are interesting in the sense that they allow us to interpret what this linear combination here refers to. Now let us assume here that this here holds true and that this here is still up in the air. We don't know for sure whether or not RU is going to be equal to ST, and there's a reason for that, because keep in mind RU and DU here, right, are representing the probabilities of A0 and B0 and A1 and B1 respectively, right? And they're talking about these qubits here. Now we have assumed up until now that these qubits are entirely independent of one another, that the coin flip does not affect the wheel spin, the wheel spin does not affect the coin flip. And for the most part, if Alice and Bob's qubits were always unentangled, that would be true, but if they were entangled, we've got to have a way to determine that. That's what we're going to do now with this essentially this linear this linear combination that we have here from our tensor product. Now remember, from here on out, we are going to be treating the R, S, T, and U as the probability amplitudes. And so what that allows us to do is investigate the two possible cases. Case one is that RU does indeed equal ST, which means in this case that the probability of getting A0 and B1 and A0 B1 and A1 B0, right, just naming all the possible combinations out there, right, the probability of getting those do indeed hold true regardless of the case. And so we can say with certainty here that Alice and Bob's qubits are not entangled. Make sure I spelled that right. All right, and so this gives us a way to check and make sure. All right, so if we have a linear combination and we don't entirely know if this 2-qubit system here is entangled or not, we can see is RU, right, equal to ST. It's just a check. Now our second case here is case 2, right, where RU does not equal ST, and this multiplication here, this statement here, what we end up saying essentially is just the opposite. So Alice and Bob's qubits are indeed entangled. They are entangled, and the question, of course, is why? Right, now keep in mind with these events, as we assumed before, assuming that their qubits are not entangled, then we can say that R here, right, represented by C0 and D0 will remain constant, which means that regardless of whatever it is, the C0 and D0 and C1 and D1 won't change, regardless of whether we're considering a multi-qubit state, right, a multi-qubit system, or a single qubit system. However, if this multiplication statement does not hold true, it means that at least one of these factors at the very least has changed. And when this alteration occurs, it tells us that there is something here affecting the probabilities, right? So this is equivalent to saying, hey, I'm going to flip this coin, but based on this coin flip, I'm going to be spinning one of two different wheels. And so that means the outcome, right? The outcome has been affected, which means between the start of our calculations with our single qubit systems prior to the tensor product and afterwards, there has been some change if these qubits are entangled. And so that's just a way to double check. And so simply put, that is how you can essentially take these qubits and take the orthonormal bases they've been represented with, and essentially take these qubits, use the tensor product, and use them to represent a multi-qubit state. And this is just a brief recap. And going on from there, you can use it to represent a multi-qubit state, and then using the formula that we have on here, whether or not, and checking if the first, right, RU is equal to ST, right, it allows us to say, hey, looking at what we have here in this case, are these qubits in this multi-qubit system that we're considering, are they entangled? And that's the question that we can ask, and allows us to answer it based on this information that we have. All right, so that's all for today. If you have any questions, again, please do not hesitate to reach out to the Q-munity Tech website or to us here. And as always, stay curious and keep on learning. Thank you.